Time is 2:30, so let's get started here. So project number 2 has been handed back since we last talked. Were there any questions regarding it? Okay. Project number 3, I posted that to the course website. You should have got an announcement about that. It is due March 6th at noon. We will spend some time discussing it shortly. Are there any questions before we get going here? Okay. So we were talking about this tomato spotted wilt virus. We were talking about an example associated with it. And it just so happens I was watching TV this weekend. Backyard Farmer, if you've ever seen that great show here. It's created by UNL. Perhaps I'm showing my age, but yes, I do watch it. Anyway, so they happen to have a segment, a very, very short segment, talking about tomato spotted wilt virus, what it was. And so I thought I'd just begin class by briefly just showing you the corresponding video. So this was actually filmed, probably about 200 feet in that direction.
You know, the tomatoes, once you peel back the skin, we don't have a disease issue. And then the last disease we commonly see in tomatoes is a viral disease, and that's tomato spotted wilt virus. Once we get that fruit development setting on, the fruit, instead of being that nice red color that we're after, it's going to be blotchy. We're going to have blotches of red, yellow, and oranges on that fruit. You can still eat the fruit, it's no impact to you, but the virus can move from one tomato to the next and when we have thrips present. So we usually recommend removal of those infected plants and look at thrips using sticky traps to determine if an insecticide application is actually necessary to control the insects in your garden.
Okay, notice how she was talking about thrips, just like what we are. Okay, so at least, that puts it a little bit in more context than what we had seen previously. So this is what the data that we have. We have 2 different infestation methods, which we just simply call 1 and 2. We also have a control method, a way that we're trying to control these thrips. And C is equal to chemical control, B is equal to biological control, and N is equal to none. So what we have here are 2 different qualitative variables, and we're trying to estimate the probability that a plant becomes infected. So there were a number of greenhouses set up where there was 100 plants, and virus H is our response, which denotes then how many plants became infected. Okay, so that's the data that we've been looking at. And so we estimated a model using the GLM function as you would normally. And what R does is automatically create indicator variables create indicator variables with respect to these qualitative variables. So for example, with control, there are, so it says 3 levels. There are 2 indicator variables associated with it, 1 corresponding to C and 1 corresponding to N. The B level, the biological level, is what we often refer to as the base level, meaning that the indicator variable values are all equal to 0 for that particular level. And that's going to be very important coming up, because now we're going to talk about, or in about 10 seconds, we're going to be talking about interactions. First of all, there's the actual estimated model. So again, notice how we have indicator variables in the model, such as infest2, that correspond to a qualitative variable. And then eventually, if we wanted to actually add an interaction to the model, we would just do it as we would expect. So infest and control. And what R does is simply multiplies the indicator variables together from the corresponding main effects for the qualitative variables. And this is the actual model that we ended up with last time. Okay, now we get to where we left off. We're going to talk about odds ratios, because now what we like to be able to do is that we have these qualitative variables in our model. We want to be able to interpret their effect on the response. Now you might be thinking, well, let's actually take a look at an example first. So let's say I again have a 4-level qualitative variable. This was the first qualitative variable that we looked at. And it has levels simply A, B, C, and D. If you remember this table that we had before. So with it, I'm going to create 3 different indicator variables to represent this 4-level qualitative variable in our model. Notice that A is the base level. So to represent them, this qualitative variable in our model, here are my 3 indicator variables shown there. Now previously when we found odds ratios for simple models, all we did was simply take e raised to the beta power. So let's talk about, well, what does e to the beta 1 actually represent in terms of these odds ratios? Now the intuitive answer is probably, well, it's comparing b to all the other levels of our qualitative variables. So, you might say something that looks like this. The odds of a success are e to the beta 1 times as large for level b than all the other levels. Again, x1 represents the level b. So you may say that, but that's actually incorrect. So let's talk about then, well, what does e to the beta 1 actually represent? Well, it goes back to basic principles of what an odds ratio is. So let's first calculate the odds of a success when you're at level, let's say, B. So here's my model, e raised to the beta 0 plus beta 1 times 1 plus, and notice the other indicator variables are 0. So those betas fall out. You're left with e to the beta 0 plus beta 1. Now again, this e to the beta 1 that we saw before, if I were to get that as an odds ratio, then what do I need to divide e to the beta 0 plus beta 1 by? Well, the answer's already there. The odds at A. So I could take e raised to the beta 0 plus beta 1 times 0 plus beta 2 times 0 plus beta 3 times 0. And I wrote this rather poorly. Everything else is 0 there. And so that's divided by e to the beta 0 or e to the beta 1. So e to the beta 1 is not a comparison of the odds for level B versus everything else, but instead it's a comparison of B to A. So now you see better probably why A is thought of as a base level. All of our comparisons are essentially being made back to level A, since the indicator variable, or I should say the indicator variables, are all equal to 0. So then the correct interpretation is then that the odds of a success are e to the beta 1 times as large for level B than for level A. You can do similar then interpretations for taking e raised to the beta 2. So you're comparing level C to A. Also, e to the beta 3 is comparing D to A. Well, what happens though if you want to compare B to C? You can still do it. Again, it goes back to the basic principles about what an odds ratio represents. So I could look at the odds corresponding to level B, divide by the odds corresponding to level C. Notice my indicator variable, x2 is equal to 1. And look what happens. Some of the betas fall out. So beta 0 and beta 0 fall out. Beta 3 was already out because you were taking x3, which was 0, times beta 3. And then, well, it's just e to the beta 1 minus beta 2. That's your odds ratio. So you could do an odds ratio for level B to D, which would be e to the beta 1 minus beta 3. Level C to D, beta 2, e to the beta 2 minus beta 3. Okay? Are there any questions? Okay. Well, let's say that we wanted a walled confidence interval for the odds ratio comparing level B to level C. And so as you might expect, we first find a confidence interval for beta 1 minus beta 2. So we would take, first of all, well, how about we just do this immediately? E raised to the beta hat 1 minus beta hat 2. Then what would be next?
Plus minus 3 quantile.
Yep, plus minus the 1 minus alpha divided by 2 quantile from a standard normal times what?
Variance.
Square root of the estimated variance of what?
Difference.
The difference, yep. Estimated variance of beta hat 1 minus beta hat 2. So how would you find that estimated variance? Yeah, go to the variance covariance matrix. So you would take, I guess it doesn't hurt to write it out. So I'm going to highlight this portion there, draw an arrow, kind of. That's equal to the variance of beta hat 1, then what?
Plus the variance of beta hat 2 times the covariance.
Minus 2 times covariance of beta hat 1, beta hat 2, because we have a negative 1 in front of that beta hat 2. Okay? So again, you just go to your covariance matrix, and there you go. Not too difficult. Hopefully, we've done this kind of stuff before. Hopefully it's becoming, rather simple. So now let's apply these ideas to this tomato spotted wilt virus example. Okay, so previously we found the interaction to be important for this data set. I'm going to first take a look at this without the interaction term in the model. It's just for demonstration purposes I do that because I think it's just going to be easier because the model has less terms in it. So here's my actual estimated model that we had previously without the interaction term. So if I want to find some, and we're going to focus on control methods. So remember, control has 3 different levels: B, C, and N. Biological, chemical, none. And so if I just extract from our previous model, if I just extract the beta hats, in fact, I'm just going to look at the third and the fourth one, and take e raised to that power, we get some odds ratios. Also, I can subtract the 2 beta hats, so beta hat 3 minus beta hat 2, and I get an odds ratio. So let's just pick one of these odds ratios and interpret it. Word is not responding. Respond. There we go. Thank you. We're going to look at this one right here. So that was e raised to the 0.5152 power. The estimated odds of plants showing symptoms, basically that's what the virus 8 variable represent, that basically came down with the disease. The estimated odds of plants showing symptoms are 1.67 times as large for using no control methods than using a biological control. We're comparing level N to the base level, which is level B, where the infestation method is held constant. Remember, you have to add that because the infest variable is in the model as well. Now, as we've seen before, there are a number of different ways then to interpret this exact same odds ratio. And perhaps a better way to interpret it is in the context of reducing the proportion of plants. Because after all, that's probably why this experiment is being run. Because you want to know if maybe using a biological control, using a chemical control, does this help reduce the probability or the odds that these plants come down with a disease? So because of that, though, you could look at the odds ratio in a different way. Just simply invert the odds ratio. The estimated odds of plants showing symptoms are 0.5973 times as large for using a biological control than using no control methods. Thus, using spider mites, which was the biological control, is estimated to reduce the odds of a plant showing symptoms by approximately 40%. So, there's probably other ways to interpret this too, but I think especially that 40% is, very important. Will be very important to the researcher. Are there any questions? Well, again, to do the no control versus chemical control. Now, remember we have indicator variables for those too. Remember what we did was we took e to the beta hat 3 minus beta hat 2. We got 3.7. Okay. Excuse me. So here's a question. Which method, B or C, reduces the estimated odds more? Let's go back to all three of them. I hear someone say C. Why? Because what? Well, yeah, you could look at the coefficient and see that too. Yeah. I guess I was hoping that you would look at the odds ratios, since we were talking about odds ratios. But yes, you are right. So we're looking at, well, which one's better, B or C? So we can look at then the odds ratio comparing B to C. And that odds ratio is this one right here. So 0.45. So remember, in the numerator would be C, the odds for C. The denominator will be odds for B. So what this is saying that the odds for B are higher than they are for C. But you have to think about what are the odds here. It's the estimated odds of coming down with the virus. Okay? So since the odds are smaller for C, because that was in the numerator, then that says that you would prefer C. Okay, so how can we find confidence intervals? I think once you get to these more complicated models, such as when you have qualitative variables, and especially once you start introducing interactions, I think the easiest way to do this is through using the MC profile package. Either getting the profile likelihood ratio intervals or the Wald intervals directly from that package. So in this particular case, what I'm going to do is show you how you can find the odds ratios for comparing C to B, and then also the N to B as well. And remember, for C to B, all we need to do is look at beta 2. For N to B, we need to look at beta 3. So what I'm going to do with the MC profile package is create a matrix called K, where I'm just going to pick off those corresponding betas. So here are my columns, what they represent, beta 0 through beta 3. And so notice the first row is going to give me, going to help me find a confidence interval for beta 2. The second row is going to help me find a confidence interval for beta 3. So I put that into K. I use my MC profile package to calculate a whole bunch of -2 log lambdas. And then I use the confidence function to help me find the confidence intervals. Again, notice I use a just equal none. I'm not going to control the family-wise error rate, although obviously I could. And so here are my confidence intervals for the betas. So the top one's for beta 2, And the bottom one is for beta 3 in terms of the confidence intervals. We want e raised to the betas. So here are then, after I use the exp function, here are my confidence intervals of interest. So for C to B, the odds ratio is between 0.35 and 0.58 with 95% confidence. To do the walled intervals as we've done before, I can use the walled function now with that linear.combo that we had created above. And my walled intervals are very similar. Again, the reason being is because, remember, we have 100 plants per combination of the controlling method and the infestation method. It's because of this stuff up here. Oops. So I mean, I know the order of my beta hats because I specified the model. And so because of that, since also I know since I've actually, let's say, derived that confidence, since I've actually derived the odds ratio, I know I need beta 2. So what I did was I wrote out, the ordering of the betas. So that row there allows me to pick off a linear combination of my betas. Are there other questions?
So the beta, there contains information from both variables.
Well, the beta 2 is basically comparing C to B, if that's what you're talking about.
No, beta 0.
Beta, what about beta 0?
Yeah, that contains information from the infest variable and the control variable.
Yes, yes it does.
But that doesn't matter because we don't use that.
It falls out. When we do the expression, it just falls out. Other questions? Okay, so if I were to compare level N to B, we see that the interval is 1.29 to 2.17. It's this one right here. So we are not with 95% confidence, the odds of plants showing symptoms are between 1.29 and 2.17 times as large when using no control methods than when using a biological control. So what that says is that doing nothing is going to increase the odds of coming down with the disease, essentially, in comparison to using biological control. So if you wanted to control the thripes, use a biological control. I also invert this odds ratio just to give you a different perspective as well. And perhaps this might be more of interest because essentially doing nothing is almost like, I'm going to use this word again, a control in an experiment. Now you could do some of this stuff, some of these simple intervals, like what we just did here without using MC profile and just use the regular old confident function that actually exists outside of the MC profile package. Confident is actually a methods function, and we originally were using the confident.glm function in class when I first introduced it. And then once we got to the MC profile package, we were using confident.mcprofile. So again, how R works is going to look at your object that you pass into it and find the class. And depending upon the class, that's the type of method function that's run. So in this particular case, the object I'm passing in there is the results from my model fit. It sees that it has a class of GLM. So the confident.glm function is the one that's actually running in this particular case. The problem with using this particular confident function is that, notice it's only going to find intervals for just like beta 1 or beta 2 or beta 3. It's not going to find linear combination. It's not going to find confidence intervals for linear combinations of the betas. That's why we need to use the MC profile package. Also, how about if I were to use a walled interval, just for demonstration purposes? I'm going to do this with the MC profile package because it's, again, nicely set up for linear combinations of the betas. So let's see here. I'm sorry, I'm getting ahead of myself. Yeah, I'm sorry, we're going to do profile likelihood ratio interval first. I saw the wall, and it's like, wait a second, I thought I was doing all, mostly profile likelihood ratios in these notes. Okay, so again, here's beta 0, beta 1, beta 2, beta 3. The coefficients on them and what we need. And in this particular case, to find our confidence interval, we're going to find e to the beta 3 minus e, we're going to find e to the beta 3 minus beta 2. So what this is going to do is compare the none to the chemical category. Again, none to chemical. I know that from what the indicator function, what the indicator variables are in our model. So it's the same kind of code over and over again. Here's my actual interval, 2.8 to 4.9. So again, what this is saying is that chemical is going to control better than doing nothing at all. And even, to some respect, even more so than if using biological, given that interval compared to the previous interval that we looked at. Okay, just a little quick note here. You notice I use MC profile essentially twice, where there's 3 possible odds ratios that we could find, and I decided to use MC profile twice. It was more, the first time was because the intervals were easier to find, because it was only involving 1 beta. And then the second time we used 2 betas. In practice, what I would do is just put everything into 1 K matrix and just use MC profile once. Make a note to myself for just a second. Now, you could actually find these intervals without using MC profile. In terms of, find the walled intervals without using MC profile. I'll let you take a look at the details on your own. Basically, it's just a matter of plugging in or programming in the formulas that we've seen in the past. In fact, when we, about 5 minutes ago in class, I said, well, let's write out the walled interval. This essentially is what that's doing. I think it's more difficult to do it that way, but you're welcome to do it. Also, I give I guess you could say a little trick of how to find these intervals without MC profile in terms of all the profile likelihood ratio intervals. You can take that look at that on your own. Yes.
With the covariance matrix, if you do the 2:4, 2:4, exactly. Is it the second row in the 4th column?
Yep. Yep. Yeah, I mean, the row number is always first, the column number is always second. Okay, so how can we do this then with an interaction? Here's our model that we had previously. So here's the 2 interaction terms that are formed from simply taking the indicator variables for both qualitative variables and multiply them together. What I would like to do first is find an odds ratio comparing level N to level B. And since I do have an interaction, I have to specify now, well, what is my level, my infestation variable? How about I say level 1? So infest2 would be equal to 0. So here's my odds of a success, you could say. I'm going to specify C equals 0 both times. So what that means is then this infest2 variable is going to be 0. Now since I'm comparing level, the n level, I'm sorry, I did that poorly. Let me restate that. Let's just start it all again. Okay, infest2 is equal to 0, so that means that's going to be 0 up there. So that beta is essentially going to fall out of my model. N is equal to 1, so there's a 1. And C is going to be a 0, because we're not comparing to C, we're comparing to level B. So that's going to be a 0. Now look what happens now when we have the interaction. C, again, is a 0. Infest2 is also a 0, and infest2 is equal to 0 as well. So when I were to calculate then the odds of a success at level n, infest2 equals 0, I get e raised to the beta 0 plus beta 3. Because the only thing that remains is this and this. Now, if I look at the denominator, notice n's equal to 0, so that's why I only have a beta 0 left. And so then what's my odds ratio? E to the beta 3. Well, what happens then, do some erasing. What happens now if I look at the odds ratio where infest2 is equal to a 1? There we go. Let me erase that too. Well, now to find the odds in my numerator, notice I have infest2 is equal to 1, C is equal to 0, N is equal to 1, N is equal to 1, infest2 is a 1, infest2 is a 1, C is a 0. So look what I'm left with, the beta 0, the beta 3, and then the beta 5. What I'm actually highlighting there are the beta hats, but I just worded in terms of the betas. So, oh, I'm sorry, also the 1 as well. So now you see I have the 4 betas down there. When I need to find now the odds with respect to infest1 equal 1, I'm sorry, infest2 is equal to 1, and also control method of B, look what happens. This beta disappears, and that beta disappears as well. So that then when what you're left with then for the odds ratio is e to the beta 3 plus beta 5. Well, let's actually use MC profile with this. So that first odds ratio where we just had e to the beta 3, when I find my K matrix, I only need to specify for that beta 3 column. When I find now my second odds ratio that we just talked about that had beta 3 and beta 5, and I specify a 1 for the beta 3, beta 5 column. On your own, you should try to look at all the other combinations of these odds ratios. So, what we did here, we compared N to B. We'll compare C to B at infest2 equals 0 and infest2 equal to 1. That's the next 2 rows. And of course, Word is not responding for me. It's being difficult. So these 2 rows that I'm highlighting here are comparing C to B, where the first row in that area is infest2 is equal to 0. And then the second row is infest2 equal to 1. The last two rows are comparing n to c. The first of those two, infest2 is equal to 0. The next one's infest2 equal to 1. Page, maybe I should have brought this up, page 116 shows the final results that has everything in the correct order. So you can see figuring out all these odds ratios can be kind of a pain. You know, it's not automatically done for you, but this is the best way to do it. You know, you have to really know what you're doing with these odds ratios. And you know, for those you've taken like a Stat 802, where you've done a lot of ANOVA models, where you're finding contrast to compare means, this is almost like the equivalent. Because we're kind of doing the same thing. So we're trying to make comparisons amongst different treatment levels. And you know, depending upon how a course like Stat 802 was taught, hopefully, you know, the professor took the time to, you know, essentially write out a matrix like this so that you could see how everything is connected in terms of trying to find combinations of the parameters of your model. Okay, so in the end, this is all the odds ratios that I get for the profile likelihood ratio intervals. And let's see. So we can see, for example, when if I'm at infest level, infest2 equals 0, look at my odds ratio, it's all above 1. But then when I go to infest2 equal 1, my odds ratio confidence interval contains 1. So notice that the effect that we have here of this control qualitative variable changes over the levels of the infestation method. That's basically the definition of what an interaction does. And we see this here. You know, the next set of odds ratios, you see a very similar thing as well. But then the last two odds ratios, notice how the intervals are essentially about the same. So what that's saying is it doesn't really matter for infest method with respect to the C versus N combination, comparison. Next are the walled intervals. See those on your own. Okay. So I feel as though I'm almost kind of repeating myself because it's the same kinds of applications of MC Profile. I have some more interpretations, you know, just using our standard methods as before. So I don't feel as though I need to, you know, read through all this. You know, I put this level of detail here in the notes so that anticipating that you would need to read some of this on your own and to try to be somewhat complete. So some final comments on page 118. So more interpretations need to be done than what I showed there. In particular, you know, you should look at the infest variable for fixed levels of the control variable. So before we were looking at levels of control for fixed levels of infest. Now you need to go the other direction to have a full interpretation of this model. You would need to do that. If you didn't want to control the family-wise error rate, well, I'm not going to emphasize that in this class. There are ways to do this with the MC Profile package, and I've kind of mentioned this before. You know, take a look at my book for how to do that. It is a good thing to do. It's just, you know, we obviously have time restrictions, and that's why I don't necessarily usually emphasize it. Okay. Are there any questions about this section before we go on to the next section? Actually, before we do that, let's talk about the next project. Okay. So similar format to before, you can work in groups of up to 3. So you might remember number 1G of the last project, which said, suppose you, and let me back up and talk about number 1 first. So number 1 on the last project allowed you to use the treatment, which was essentially Olestra or regular for the type of potato chips, to predict were there side effects or not. And in number 1G of that project, I said, what happens if you also had some additional information about the amount that someone ate? And the right answer for that particular problem was, well, simply include it as an explanatory variable in the model. That's it. That will allow you then to look at essentially the results from this treatment by controlling something that's very, very important. How much did one eat? In particular, some of the theory behind the problems with Olestra was that since it was used this fat substitute, so you would be, I guess, ingesting, or what's the right word to? You'd be retaining, let's say, less of the fat from the potato chips when you eat it. One of the hypotheses was the reason why people were having side effects is because they were wanting to eat more potato chips than they would have normally, because they know that they're not going to necessarily retain the fat as they would have previously. And so that was a theory behind it. So it just makes sense then that in any kind of controlled experiment like this, you want to have information about exactly how much do they eat. And so I thought that would be an interesting follow-up or to that. So what I decided to do was, since I don't have that information about how much they ate, I simulated some data. So here's the data set that you're going to be using. You can download it from the Graded Materials webpage. The response and the treatment is exactly the same as in the previous projects. Excuse me. CHIPS is simulated. Now, what I was hoping was to basically kind of confirm that what people were kind of thinking, that people would eat more, and that's what was actually causing the side effects. But I have to admit, I was having problems actually simulating data exactly like that. So while it kind of occurred, there was you could say a side effect that ended up happening with the data itself that you'll notice when you analyze it. So while I tried to make this as real as possible, just realize it is simulated data, and there's some perhaps unrealistic aspects to it. Okay, so also, one thing that I was hoping that you would get out of number 1G of the last project was the fact that we can't look at the data in a binomial form anymore, because individuals could eat a different amount of chips. So because of that, we need a binary response format, and that's what I have here. What else? Notice that treatment obviously is a qualitative variable, so that's in the context of what we've been talking about. Chips is in terms of ounces, so somehow they were able to actually measure the exact number of ounces that somebody ate. Originally, those were going to be the number of chips, which I would think might be easier to count, but it ended up being ounces. The response variable is a 1 for side effects, 0 for no side effects. Okay, so let's look at the following. First of all, part A, use the levels and contrast functions, which we talked about last Thursday, I believe, or maybe even the previous class period. Use those functions to show how R will count for the treatment variable. That should be fairly easy. There's going to be an indicator variable created. I want you to show me, how R is going to do it, and then verbally actually say it. Part B, I just threw that in there just to confirm to you, in case you just didn't believe me, that indeed the response and treatment were exactly the same as what you've seen before. So this model that you're going to estimate here should be exactly the same as from project number 2. Should be easy. Part C. Okay, now this gets into the modeling with the amount of chips. So take the amount of chips, so the chips variable, type of chips, that's the treatment variable, and their interaction, put them in a model, and estimate the logistic regression model, and state the model correctly. Part D relies on this next section that we're going to start shortly, so I'm not going to discuss it right now. Part E says, well, let's perform a likelihood ratio test to determine if there is an interaction between the amount of chips and the type of chips. Part F is motivated by, if you remember the distance and wind model to estimate the probability of success for a place kick. Remember how we did a plot and you could see how the interaction actually appears on the plot? That's what motivates F here, where now you're going to put chips on the x-axis, the estimated probability of side effects on the y-axis, and then draw 2 lines, one for treatment olestra and one for treatment regular chips. Oh, Word's not responding once again. What's going on? There we go. Okay, so part G. Now let's use odds ratios and profile likelihood ratio intervals to thoroughly interpret the effect that type of chips has on whether an individual has side effects. So similar to what we had just done with the tomato spotted wilt virus example. Part H is the next section. Part I is the section that we're going to talk about in class that follows that. And then also part J does too. So while you can't do everything right now, you'll be able to get a very good start on it. Are there any questions? Okay. Then let's go back to page 119. Okay, so we have to use a numerical iterative method to come up with these beta hats. These iterative methods do not necessarily always converge, meaning to obtain a set of beta hats that would not change from additional iterations. And so the purpose of this section is to talk about how does R actually determine has convergence occurred? Also, to talk about when convergence will not occur. And then lastly, what to do if convergence does not occur. Okay, so when I originally introduced the idea of these numerical iterative methods, what we were basically doing was looking at, let's say, at iteration 0, or you could say, come up with some kind of initial estimates of the betas. And let's say that we just have one explanatory variable in our model. It's continuous maybe, and we get a beta hat 0 and a beta hat 1. And so at iteration 0, we come up with some values. And then we go to, let me put iter here. And then at iteration 1, so the first time through this numerical iterative method, you come up with a new set of estimates. And then you compare iteration 1 to 0. If there really hasn't been any change, you're done. You have converged. If there has been change, you go to iteration 2. And you repeat this process of coming up with hopefully better estimates and comparing the estimates that let's say, iteration k to k minus 1. And again, you converge when these beta hats don't change a lot. R doesn't look at these beta hats directly. Instead, what it does, it forms a one-number numerical summary, you could say, of all the beta hats in the model. And it does it by looking at the residual deviance. Can someone tell me what the residual deviance is? Not the model with no parameters. So excuse me?
Which saturated.
Yeah. So it's the model of interest compared to the saturated model. It has, let's say, as many parameters as possible. That's what the residual deviance compares. And it does the comparison through using a likelihood ratio test, the -2 log lambda. Okay? So let's call the residual deviance simply G. You often see people use the letter G. I don't know why. But people often use the letter G with a deviance statistic. And what R does is this. At iteration, and let me back up. So this residual deviance then is kind of an overall one-number measure or summary measure of all the beta hats. Why? Well, because remember those beta hats go into producing your pi hats, and then the pi hats are used for your likelihood ratio. For your likelihood function, and thus your likelihood ratio. Okay, so at iteration k, the residual deviance is compared to what it was in the last iteration, and then the absolute value is found. Now, depending upon the context of your data, it's hard to determine, well, is this a large difference or a small difference that you get there? So, excuse me. So what happens is you divide by G at the current iteration so that you get a relative difference. And R just throws in an extra 0.1 in there as well. So you look at that, you look at essentially what's a relative difference. And what you're hoping is that relative difference is small. Very small. If it's very small, then you said you have converged. Well, how small? Well, what you could do is set some number epsilon. Let's say maybe epsilon might be, let's say, 0.0. Actually, R uses 10 to the -8th power. So 0.0000, well, you got 7 zeros and then a 1. That's what R uses for epsilon. So if your difference is that small, you are done. You have converged. Congratulations. If, though, you have not gotten below that threshold, you keep on going. And you keep on going until you reach some maximum number of iterations that you set. Or you go with the default, which is 25 in R. That's how R determines convergence. So if you reach the maximum number of iterations and you still have not got underneath or less than that epsilon, then R will say, uh-oh, you have not converged. So if you have not converged, should you use your model that you got? No, because of course if you went another iteration, the beta hats are going to change. And then your interpretations of your model will change. So you should only use a model when you have converged. There's actually some situations you shouldn't use a model where R says you have converged too. And I'll show those to you shortly. So to control epsilon, if you wanted to use a different epsilon than what's actually given to you in R, and it doesn't happen often, but if you did, you can use the epsilon argument in the GLM function. Well, what happened maybe more often is you can change maxit, which stands for a maximum number of iterations, that argument in GLM. You can change it to something more than 25. Where would you want to change it? Well, let's say you don't converge in 25 iterations. The first thing that you should probably do, try a larger number of iterations, see if it works. If it doesn't, then we'll talk about what to do. Also, you can watch the convergence happen right before your eyes by using the trace argument, which allows you to see each of the G's being printed. So let's actually take a quick look at an example that does this. We're going to go back to the Placekicking data set once again with only distance in the model. So I'm going to use exactly the same GLM function call that we've done before. It's about on page 120, except for I'm going to put trace equal true. I'm going to reduce my epsilon. I would only do that basically for demonstration purposes. And then also I'm going to increase my max it to 50, just for demonstration purposes. And so what we see here then is that R will print the iteration number and also the residual deviance. So the 775.745 is G with a superscript 5. Convergence occurred at the 5th iteration. Why? Well, compare G, oops, I guess I already did that. Compare G at the 5th iteration to the 4th iteration through that expression that I gave you before, and you get 1.3 times 10 to the negative 7th power. Remember what I set epsilon to be, 0.0001. So, based upon this epsilon, convergence has occurred after 5 iterations. Yes?
Is there any rule that how big the epsilon should be?
You know, there's not necessarily a rule, just that, you know, obviously you want it to be small. I mean, if you're really concerned about how small it is, what you should do is try a few different epsilons and look at the practical meaning of the changes in the beta hats. Now, at iteration 4, if you were to, come on, Word. At iteration 4, if you were to compare 4 to 3, go through the calculation for what R uses to determine convergence, you will see that the criteria was at 0.00012, which was above what we had set epsilon to be, so that's why you went to an iteration 5. And you can try this on your own too. Suppose you set max it to be 3. Then you can see what R tells you. Well, algorithm did not converge. Now again, that's just for demonstration purposes. One wouldn't ever actually do that for real. Okay, so now you know a little bit about how R determines convergence. Let's talk about the situation of you don't get convergence. As I already said before, one of the first things you should do is just try a large number of iterations. Okay? Now, if that doesn't work, then what that says is that there's probably some fundamental problem with your data and using logistic regression. You know, there are cases where simply logistic regression is not going to work with that kind of data. And there are alternatives that you could use. We'll talk about those shortly. First, though, I want to talk about the most common problem that occurs by far with logistic regression. And that is you have something that's called complete separation in your data. What that basically means is you can think of it this way. This is the easiest way to think about it. Your response is either a 0 or 1. Suppose you have only one continuous explanatory variable, x. And x is always small for y equals 0s, and always large for y equal 1s, such that x essentially perfectly discriminates between the y equals 0s and the y equal 1s. So if you have a small x, you know you're going to get a y equals 0. If you have a large x, you know for sure you're going to get a y equal 1. If that happens, you're going to have convergence issues. You'll see a nice plot that shows why that occurs shortly. Now, you'll often see another warning message that pops up in these situations, and that is fitted fitted probabilities numerically 0 or 1 occur. What that means is your pi hats are often being estimated by your model to be 0 or 1. Doesn't necessarily mean all your pi hats are 0 or 1. It just means some of them are extremely close to 0, extremely close to 1. And think about why that should occur. If you have complete separation, well, you know that for x large, y should be 1. If x is small, you know y should be 0. So you would expect your pi hats to probably be something like that. So that's why that occurs. Again, we'll have a nice little plot that demonstrates that shortly. No, I guess right now. Okay. So what I've done is just made up a data set. Of course, you shouldn't make up data in practice. I guess unfortunately I've given you 2 examples where I've made up data today. But it's for educational purposes. So let's say that I have this following data set here, where I have one explanatory variable. And if it's less than 6, y will always be at a 0. If it's greater than 6, greater than or equal to 6, y will always be equal to a 1. And so here's my data in a data frame. And then I fit my model, just using normal methods. I'm going to let trace equal true so I can follow the iteration process. And take a look at what happens. It gets to iteration 25, which again is the default for GLM. And then I start getting warning messages. Uh-oh, did not converge. Fitted probabilities numerically equal to 0 or 1. Okay? Here are my beta hats at my last iteration. Of course, I would never want to use those in practice. But what we can do is graph the model that was shown to us on iteration 25. And that's what's shown on the left-hand side here. So the open circles are my actual observations. What's shown in red is my model at iteration 25. Notice the separation of the points. This again completely separates out the y equals 0s and the y equal 1s. And so what the model is trying to do is essentially get a slope that's equal to infinity. Here's my slope of my line. So essentially my beta hat 1 is positive infinity. Is R ever going to reach infinity? R is pretty good, but even R can't reach infinity. And so it's going to keep on going and going and going, essentially without stop. I purposely say the word essentially. You'll see why coming up. So complete separation is bad for trying to find maximum likelihood estimates for your betas. Okay. Also, you can see why you see that message of fitted probabilities equal to 0. Again, what that means is your pi hats are equal to 0. Fitted probabilities equal to 1. That means your pi hats are equal to 1. You can see the line there. It's showing 0 and 1. Is there a question? Okay. But there, you know, excuse me. But what happens if you were to try a larger number of iterations? After all, I told you to do that if it doesn't converge. If you did in this case, at iteration 26, R says convergence. You know, the first time I ever saw that, I was like, wait a second, is there a problem with R? No. The problem is how convergence is being decided upon. Because remember, these beta hats, they're changing, right? They're going to keep on changing for more and more iterations. But we're not looking at the beta hats, let's just say, directly to determine convergence. We're looking at our likelihood ratio test statistic, that residual deviance. And eventually you're going to get to some point where all your pi hats are going to be extremely close to 0, extremely close to 1, and any more change in the beta hats, are they going to change the pi hats much? No. Just try it yourself. Just write out, or you can do it in R, write out what your model would be for a fixed set of x's. And eventually, if you keep on increasing, you could just do beta hat 1. If you keep on increasing beta hat 1, your pi hat is not going to change a whole lot. 0.99. Next time's 0.999. Next time's 0.9999, and so on. And so because of that, your residual deviance itself is not going to change a whole lot. That's why R is saying convergence, even though your beta hats itself had not converged. Because if I were to use a smaller epsilon to force us being able to use a larger number of iterations, you will see the beta hats will continue to change. So that's the problem. So the main thing is this. If R tells you you have not converged, well, you have not converged. If R tells you you have converged, well, likely you have, but you have these situations that you have to worry about. How can you make that determination? Well, essentially you look at the size of your beta hats. Again, as I told you, these beta hats will keep on getting larger and larger and larger. If you see some issues with that, then you might have complete separation. What could you do? If you're worried about it, well, then force R to go a larger number of iterations and look at your beta hats. Are they changing or not? If they're not changing, okay, you have really converged. But if they are changing, then you're likely falling in this kind of a scenario. So, another issue, well, I'll get to that issue in just a second. Suppose I just change two values. So at x equal to 5 and 6, which is what we had, right here and right here, I flip a y equals 0 and 1. And notice we have what we normally see with these kinds of models, and in fact this model does converge. But, there's a possibility that you're going to get that fitted probabilities equal to 0 or 1 statement pop up, even though that's not necessarily a problem. Now, another issue then that comes up is, well, suppose you have, let's say, 5 explanatory variables. It may be difficult to figure out if you have complete separation from simply looking at the data, because you can't do a plot like this. And so that's another issue where what you might have to do if you're worried about it is force R to do a larger number of iterations to see what happens, see if your beta hats change. Okay. Are there any questions?
Is there a problem with how large you go in terms of the number of iterations that you do? Like if you go too large, above the 50 that you just shown in the example?
I mean, in terms of time, you just have the time issue.
All right.
How long is it going to take to fit the model? Eventually, you'll get to a point where no matter what you change for epsilon and whatever you use for the number of iterations, you can't go any farther. It just has to do with the precision of a computer. Okay. But by then, you should have been able to determine, there is a problem or there isn't. So what should you do if complete separation does occur? Call me? Well, no. Here are two possible options. And there's a nice little paper that talks about them. That was written about 13 years ago use what's called exact logistic regression. Now, remember how we've said that our beta hats have an approximate normal distribution to them because they're maximum likelihood estimates, right? Well, that's not the exact distribution of the beta hats. Instead, the exact distribution is something essentially discrete. It's a discrete distribution. We talked a little bit about exact distributions before with the Klopper-Pearson interval. And so what exact logistic regression does is it uses the actual exact distribution of these beta hats to try to make inferences. Take a look at chapter 6 of my book if you want to know more information. Again, you simply just don't have time to discuss everything. An alternative approach, which actually these guys recommend over exact logistic regression, I don't remember off the top of my head if it's in this paper or in a follow-up paper that they did, and that is to modify the likelihood function. What I mean by that is that, these maximum likelihood estimates in these complete separation settings will result in infinite estimates. Well, why do you have to necessarily use the regular old likelihood function then to find estimates? Maybe you could use what's called a penalized likelihood function, which essentially penalizes the likelihood function for getting too big. And you can come up with estimates from a penalized likelihood function approach. And that's a possibility. I still think, to be honest, that again, I don't remember if it was this paper or the follow-up paper. When they evaluated these two situations, the evaluation that they did, I don't think was maybe as thorough as could be done. So there's possibly a master's project out there that could be done to evaluate something like this. Okay, so some final comments then. Complete separation is actually not that bad. You might be thinking right now, oh, I don't want complete separation. But if you want to find maximum likelihood estimates in terms of interpreting the effect that X has on the response, yes, it can be bad. But there are situations where, let's say you're solely interested in prediction. Think of the Placekicking data example. If Mike Riley had a nice model that would tell you, yes, our kicker is going to make the place kick, or no, for sure, well, he would like that model. And essentially, complete separation is kind of giving that to you, because they will give you, at least with your observed data, perfect prediction. So if you take, let's say, set 873, you talk about using certain models, such as just regression models, to predict a response. And in that setting, complete separation would be desirable. Let's see now. So we've already talked about that bullet. There's ad hoc solutions out there. I recommend don't doing them because we have better solutions nowadays. But sometimes you'll still see people talk about it. And lastly, there is actually a function called GLM2 that presents some different model fitting methods that might be helpful if you're having some issues. Sometimes you can get in a situation where you are close to complete separation, and that can cause some issues. And so, some of the alternative methods I've talked about, or maybe even GLM2 might help you. Okay. Section 2.2.8 is really cool, but we don't have time to do it. Take a look at it on your own, read the chapter, but I'm not going to test you over it or read the section. Okay, so we will next talk about section 2.3, generalized linear models. And we are unfortunately out of time. Are there any questions? Okay, that's it for today.